Good afternoon, students. In the last lecture, we have completed the topics of lesson number 8, transition elements. Now, transition elements. The lesson number 8 divided into the 2 points. First, transition element, and second, inner transition elements. That is the first part of the chapter, transition elements, is completed in last lecture. Then started the second topic, inner transition elements. These inner transition elements are also called the block elements. The all elements of modern periodic table divided into the 2 block elements, S block, P block, D block, and the F block. That 3 block elements, S, P, D, you are already completed. Then next part is the inner transition elements from your block elements. Why these elements are called the inner transition elements? Because that transition elements are placed from group number 3 to 12. Group number 3 to 12 and period number 4 to 7, 4, 5, 6 and 7. That period number 6 and 7. That group number 3. This is the third series of D block elements that having the element lanthanum. And period number 7 and group number 3. There is the starting element is actinum. Right? That lanthanum having the atomic number 57. And that actinum having the atomic number 89. Right? Then there is a group number 4. That group number 4, after the lanthanum there is the element hafnium, and this hafnium having the atomic number 72 and lanthanum having the atomic number 57. Then actinum having the atomic number 89, and here is the element rutherfordium that having the atomic number 104. Then see, after the lanthanum the coming element having the atomic number 58. But in this period number 6, in group number 3 there is the lanthanum, and in group number 4 there is the hafnium with atomic number 72. That means there is the element from 58 to 71 that are not placed in the D block elements, but they are present inside the D block elements. Right? But they are present inside the D block elements. Same here, after the actinum there is the atomic number from 90 to 103. These elements, these 2 series of elements are not placed in group number 4. Right? But they are placed inside the D block elements, and D block elements are called the transition elements. So these elements, these 2 series of elements are called the inner transition elements. They are called the inner transition elements. Then their actual position of inner transition elements in modern periodic table is these 2 series. They having the actual position in group number 3 and period number 6 and 7. The first series having the actual position group number 3 and period number 6. Then second series having the actual position in modern periodic table group number 3 and period number 7. Right? After the lanthanum there is total 14 elements that are from atomic number 58 to 71. This is the first series, and this first series is present at the bottom of the modern periodic table. There is the 2 series present at the bottom of modern periodic table. Each series contains the 14 elements. Right? Each series contains the 14 elements. That first series started from cerium to lutetium, and second series started from thorium to lawrencey. thorium to lawrencium. That cerium having the atomic number 58 and lutetium is 71. That is total 71, 58 to 71, total 14 elements are placed in the first series of block element at the bottom of the modern periodic table. This is the first series of inner transition elements. Then there is the second series started with the thorium 92, lawrencium 103. There is total 14 elements, and this is the second series of inner transition elements. That means there are total 28 elements present in the bottom of two series that are called the inner transition elements. They are placed inside the D block elements. They are placed inside the transition elements. So they are called inner transition elements. Okay? Their actual position is group number 3. When first series elements of inner transition elements are followed by the lanthanum, and the second series of inner transition elements are followed by the actinum. So first series is called the lanthanoids and second series is called the actinoids. When you write the first series of inner transition elements from lanthanum to lutetium 57 to 71, and second series actinum to lawrencium, that is 89 to 103. Yeah? These are the two series of inner transition elements. These inner transition elements are called the block elements because inner transition elements are included in the block elements because their valence electrons enter into the F orbital. Their differentiating electrons enter into the F orbital. But if you consider small n is the number of last shell, then for the F block elements, their valence electrons enter into the pre-penultimate shell of F orbital. Pre-penultimate shell of F orbital. That means there is the penultimate shell of D and there is a last shell, N shell, that contains the S electrons. That is N minus 2F. Their valence electrons present in pre-penultimate shell of F orbital. So they are called the F block elements. In this F block, there is the first series followed by the lanthanum. So the first series is called the lanthanoids, and second series is called the actinoids. Actinoids. In these lanthanoids, their valence electrons enter into the 4f orbital, and in actinoids, their valence electrons enter into the 5f orbital. So the first series of inner transition elements are also called 4f series, and the second series of inner transition elements are also called 5f series. 5f series. Please, then see here. There is the one scientist, Glenn Seaborg. There is the one scientist, Glenn Seaborg. This Glenn Seaborg proposed a revised design of periodic table with a whole new series of elements. He proposed a revised design of periodic table with a whole new series of elements. Let me see, discovered the new model of periodic table. When he showed his design to two inorganic chemists, They said him, do not publish this design. Why they should tell him, do not publish his design? They told him that tampering with the established periodic table will affect his career. But he don't listen to them and publish his design. He later on remarked that I did not have any scientific reputation, so I published it anyway. Now we see that the elements of 5F series, from 89 to 102, these elements are fit in the Seaborg design. In the order of these elements, 89 to 102, are fit in the Seaborg design of periodic table. Okay? This is the one scientist that discovered the design of periodic table. Okay? Next, we are talking about the Yablok elements. That Yablok elements contains the two series. First is 4F series and second is the 5F series. 4F series is also called the lanthanoids and 5F series is called the actinoids. Then there are some properties of Yablok elements are given. These Yablok elements are called the inner transition elements. They are placed inside the D block elements, that in group number 3. Okay? So they showing the similar properties to D block elements. With the D block elements. Then second property, electrons are added to. For the Yablok elements, the electrons are added to pre-penultimate shell of F orbital. Okay? Their valence or differentiating electrons enter into the pre-penultimate shell of F orbital. Historically, these inner transition elements or Yablok elements are called as rare earth metal. They are also known as rare earth metal. Why they are called the rare earth metals? Because there is a difficulty to extracting them from other economically at that time. According to the history, there is very difficult to extract these inner transition elements from others economically, because lanthanoids showing similar chemical property. But this happened at very ago. But today it is very easier to separate them. It is very easier to extract them. There is one new method to extract them called ion exchange resin. According to this method, the lanthanides are easily extracted from one another. There is a next property. They are fairly abundant. They are fairly abundant. There is one example, thorium. Thorium is more abundant than silver according to mass. According to mass. There is the next one. These metals are soft. These metals are soft. With moderate densities of. These metals are soft metals with moderate densities of 7 gram per centimeter cube. 7 gram per centimeter cube. Next property for a block elements, they having higher melting points and boiling points. Higher melting points and boiling points. Their melting point is nearly higher than 1000 degrees Celsius. And their boiling points are nearly more than 3000 degrees Celsius. The next property, these block elements, or you say lanthanides, in their metallic state, they are very reactive. In metallic state, they are very reactive. They are very reactive, same as the alkali metals and alkaline earth metals. They showing the similar property with alkali metals and alkaline earth metals. That alkali metals and alkaline earth metals when reacted with water to form hydroxides. For example, these lanthanides also reacted with the water to form hydroxides. See here, we are taking F as the block element, that elements in solid state that reacted with the water in liquid state to form hydroxide plus evolution of hydrogen gas. Plus evolution of hydrogen gas. This property is similar with the alkali metal and the alkaline earth metal, but in metallic state. Here, the next property, the common oxidation state of lanthanides. The common oxidation state of lanthanides is +3. Is +3, but +2 oxidation state is also important. +2 oxidation state is also important. Therefore, in +2 oxidation state, this +2 oxidation state is very important. They all form the stable oxides. Stable oxides of type M2O3. Here M is the denotation for lanthanides, or you say block elements. They form the stable oxides of type M2O3. Then there is the next property. Lanthanides having low heat of atomization. They having low heat of atomization. First one, what is the heat of atomization? Heat of atomization is the energy required to break the metal lattice. To break the metal lattice. Why they having the lower heat of atomization than the transition element? Than the transition element. Why they having the low heat of atomization than the transition element? Because in the transition element there is a valence electrons present in a d orbital, and this d electron due to this d electrons of transition metal, they are very hard, and their crystal is not easily break. Their crystal lattice is not easily break, and that requires the higher amount of energy to break the crystal lattice of transition metal. So, transition elements having the higher heat of atomization than the lanthanoids, or you say block elements. And in comparison with the lanthanides, their valence electrons are present in the f orbital. Right? Then there is the next property. There is the two elements from the lanthanides, europium and ytterbium. Europium and ytterbium have low enthalpy of vaporization. These two elements from the lanthanides, they have a low heat of vaporization. Low heat of vaporization or enthalpies of vaporization. See, due to this property, they again resembles with the alkaline earth metals. They resembles with the alkaline earth metals, and according to their similarity, they dissolve in liquid ammonia to give. They are dissolved in liquid ammonia to form blue color conducting solution. Blue color conducting solution. Due to this property, europium and ytterbium, they having the low heat of vaporization, similar with the alkaline earth metals. Like the alkaline earth metals, these two elements are also dissolved in the liquid ammonia to form the blue color conducting solution. Then there is the next one. They are ionic radii. The common oxidation state for the lanthanides is +3. Their ionic radii decreases from lanthanum 117 picometer to lutetium 100 picometer. There is a decrease in ionic radii. Why there is a decrease in ionic radii? Because of the increase in nuclear charge from left to right. That is from lanthanum to lutetium. This nuclear charge increases because the valence electrons of lanthanides enter into the 4f orbital, and these 4f orbitals showing the poor shielding effect. This 4f orbital does not shield the outermost electrons from the nuclear attraction, and the valence electrons, the electrons present in outermost shell, they experiences the higher nuclear attraction. So their ionic radii goes on decreasing. Clear? Then see, there are some chemical properties of lanthanides are given. There is one chemical property you are already see. They are behave like the alkali metal and alkaline earth metals. They form hydroxides. When the lanthanides reacted with water to form hydroxides, the general symbol for the lanthanoids is Ln. with the water, they form hydroxides. Their common oxidation state is +3. Due to this, they form the LnOH thrice. They form the hydroxides. They form the hydroxides, that is of Ln3 plus ion. These hydroxides are ionic as well as the basic. These are the ionic and basic. Since the ionic radii of lanthanides decreases from lanthanum 3 plus to lutetium 3 plus, the ionic radii of lanthanides in +3 oxidation state decreases from lanthanum to lutetium. So, their basicity of hydroxides also decreases. So, their basicity of hydroxides also decreases. There is the question asking on this, the basicity of hydroxides of lanthanide goes on decreasing from lanthanum to lutetium. Why? Then you write first, lanthanoids reacted with the water to form the hydroxides of type LnOH thrice. LnOH thrice. That means in +3 oxidation state, the ionic radii of lanthanides in +3 oxidation state decreases from lanthanum to lutetium. So their basicity goes on decreasing. That means lanthanum hydroxide is stronger base as compared to the lutetium hydroxide. This is the strong base and this is the weak base. There is another picture. LaOH thrice is a strong base as compared to the LuOH thrice. Then your answer is same here. Okay? Then there is the next property with nitrogen. The lanthanoids reacted with nitrogen to form corresponding nitrides of type Ln capital N. Then lanthanoids reacted with halogens to form corresponding trihalides of type LnX3. Here Ln is the lanthanoid, elements of lanthanoids, LnX3. Then next with the carbon. When these lanthanoids are strongly heated with carbon, they form the carbide of type LnC2. When lanthanoids are strongly heated with the carbon, they form lanthanide carbide LnC2. These are the chemical properties of lanthanoids. Then there are again some properties of lanthanoids are given. There is the first one. Lanthanoids are soft metal with silvery white color. They are the soft metal with silvery white color. When these lanthanides are exposed in air, their shining goes on reducing. Second one, they are the good conductor of heat and electricity. in the lanthanoids except the promenthum. Except the promenthum, remaining all elements are non-radioactive in nature. All are non-radioactive in nature. Only the promenthum is the radioactive from lanthanoids. Next property, their atomic and ionic radii. Their atomic and ionic radii are decreases from lanthanum to lutetium, and this gradual decrease in atomic and ionic radii are called the lanthanoid contraction. This lanthanoid contraction is again given in brief in next topic. The next topic, the coordination number usually. Their coordination number is usually greater than 6. Typically they showing the coordination number 8 and 9 up to the 12. These lanthanoids are strongly paramagnetic in nature. These lanthanoids are strongly paramagnetic in nature. In these lanthanoids, that gadolinium, in these lanthanoids, the element gadolinium becomes the ferromagnetic below 16 degrees Celsius. Below 16 degrees Celsius temperature. And there are the higher or heavier lanthanoids. They also becomes the ferromagnetic at much lower temperatures. They become the ferromagnetic at very lower temperature. Okay. These are some properties of lanthanoids and Yablok elements. There are some reasons or some properties are asking for the exam.